Good evening, everyone. Welcome to the fourth session of live problem solving in GATE Metallurgical Engineering. I am Santhra Krishnan, and these live sessions are brought to you in association with NPTEL and PMRF. So, today is 27th of October, and it has been like past 3 weeks. We have been discussing problems from previous year GATE Metallurgical Engineering. I hope all of you have gone through the sessions, and in case you have any doubts, please reach out to me on my personal mail ID. So in this week, we will be following a similar activity. We will be discussing 4 questions from previous year GATE Metallurgical Engineering. So in case you are planning to attend the GATE examination of 2023, I suggest that all of you attend these live sessions, or if time doesn't permit, please go through the recorded live sessions in YouTube. So on that note, let us move on to this week's questions. So the first question that we will be discussing today is, for a BCC metal, the ratio of surface energy per unit area of the 100 plane to that of the 110 plane is dash. This was asked in GATE Metallurgical Engineering 2016 for 2 marks. So for this question, we need to be familiar with the surface energy per unit area equation. And once you know the equation, you will be able to substitute the corresponding values for 100 plane and 110 plane and then find out their ratio. So first, the equation. So the surface energy per unit area for a given plane has the equation delta Hs by zero point 0.5 Na into Cn of bulk multiplied by the number of surface atoms into the Cn lost by surface area, and the unit is joules per square meter. So in this particular equation, delta Hs is the molar enthalpy of sublimation. Cn is the coordination number, Na is the Avogadro's number. And here we can see there are two coordination number values. One is the coordination number of the bulk, and one is the coordination number that is lost while we are considering a given plane. Also, we need to know the number of surface atoms as well as the surface area of the given plane. So if you see this particular equation, we can see here the delta H is zero point 0.5 and Na are constant. Actually, Cn is also a constant for a given crystal, but in case we are comparing different crystals of a material, it is necessary that Cn should be present in the equation. Therefore, in our case, we will be considering only delta H is 0.5 Na as a constant, say epsilon. So once you substitute that, we will have epsilon into number of surface atoms by surface area into Cn lost by Cn bulk. This is the equation that we will be using for solving this particular questions. So please keep in your mind the things that you have to memorize is the number of surface atoms divided by the surface area into coordination number lost by coordination number of the bulk. So coming to our particular problem. See, the BCC unit cell has a bulk coordination number of 8. And here we have the 110 plane, and here we have the 100 plane. So if this is taken as the axis, we can say that this is 1, and since these are 0 and 0, it will be infinity in both directions. So this is the 100 plane. On similar grounds, we have the 110 plane. That is, we will be moving 1 to this direction, 1 to y direction, but whereas on the z direction, it will be towards infinity. So this is the 110 plane. So when we are considering these two planes, let us see their actual coordination. So bulk coordination number we already know, it is 8, right? So this particular surface has another coordination number. How? See, if you are considering this particular atom, it is in contact with this atom. So here in this picture, it is not in contact, but in reality, the crystal will be in such a format that these atoms or these entities are in direct contact with each other. Therefore, if you are considering this atom will be in contact with this atom and this atom, and on similar grounds it will be in contact with an atom on the upper plane and one on the side plane. Therefore, the coordination number of the given surface is 4 and the coordination number of the bulk is 8. Therefore, coordination number lost is 8 minus 4 gives us 4. And also the number of surface atoms. If you're seeing these particular plane, we can see that there is 1/4 here, 1/4 here, 1/4 here, 1/4 here. So these 4 will together make up one atom. That is the number of surface atoms. So that is the case. And on similar grounds, when we are discussing 110 plane, the coordination number of the surface. So here The plane is passing through the center of the crystals. Therefore, it is also in contact. This is a BCC unit cell, body centered cubic unit cell. So, body centered cubic unit cell means that inside also there is one atom present, and this particular plane is in contact with that atom as well. So, when we are considering coordination number, this particular atom is in contact with this, is in contact with what all things? It is in contact with this particular atom, it is in contact with the center atom, right? It is in contact with this atom as well. So inside this particular crystal it is in contact with three atoms. Similarly, it will be in contact with three other atoms on the next adjacent crystal. Therefore the coordination number of the surface is 6. So coordination number of bulk minus coordination number of the surface, therefore coordination number lost is what? Coordination number lost is 2. I hope it's clear. So, and the number of surface atoms, if we are counting, these four will make up one atom, and counting the center atom, the number of surface atoms will be 2. Therefore, what are the requirements of the equation we have already met? We have found out the number of surface atoms for each case and the coordination number lost for each case, and then substituting the equation the number of surface atoms by surface area Cn lost, Cn of bulk. Cn bulk we know, Cn lost we have calculated, and the number of surface atoms also we have understood. Now the surface area. For 100 plane, what is the surface area? This is actually a square. Therefore, if this lattice parameter is A0, then A0 square will be the surface area. That is A0 square. So, in this particular plane, what will be? This is a rectangle. So, it will be what? This distance into a0, right? And this distance, if you are calculating, how we can calculate? If this is a0 and this is a0, then this is the diagonal, or we can say this is a right angle triangle, and according to Pythagoras theorem it will be root 2 a0. Therefore the base of the rectangle will be root 2 a0, and this vertical height will be a0, hence the area will be root 2 a0 square. So epsilon for both, since it is a BCC unit cell of a given material, the epsilon for both will be same. They can be cancelled out. Here we have 1 by a0 for this plane, and 1 and 2 by root 2 a0 square for this one, because the number of surface atoms is 2 over here and 1 over here. And finally, coordination number lost by coordination number of bulk, that is 4 by 8 and 2 by 8. And on cancelling, finally we will be getting the value root 2. Hence the final answer is 1.414. So that is the question. I hope it's clear to all of you. So here this was the question for a BCC metal. The ratio of surface energy per unit area of 100 plane to that of the 110 plane is root 2 or 1.414. So for tackling particular this kind of questions, we need to identify first how to draw a plane. Then for BCC and FCC, we need to identify where the atomic positions are, and then we should be knowing the bulk coordination number, and we should be able to calculate the surface coordination number. And based on the way in which the plane is located, we can calculate the number of surface atoms, and once we have found all these along with the surface area, we will be able to find out the ratio. And in our particular case, for a BCC metal, 100 and 110 plane has a surface area ratio of root 2, that is 1.414. I hope this is clear to all of you. So in that case, let us move on to the next question. A simplified energy band diagram of an intrinsic semiconductor at thermal equilibrium is shown. In the accompanying table, which one of the four columns directly and correctly represents the listed parameters? Assume same effective mass for electrons and holes. So it was also asked in GATE Metallurgical Engineering 2016 for 2 marks. So it's a very, very basic question. So like actually I think it might not even need an explanation for people who are familiar with basic semiconductor material. But nonetheless, we can identify what all things we can understand from this particular energy band diagram. And then we will answer the question. So this is a normal energy band diagram. This is the direction of increasing electron energy. And then we have the state in which electrons are filled. So this is called as our valence band. and the empty state is the conduction band. When we are providing energy to the crystal in any form as heat, light, etc., electrons present in the valence band will be excited to the conduction band, and when electrons leave the valence band for the conduction band, holes will be created in the valence band. That is how the mechanism of electron hole generation works. And in this figure, we have many terms, right? So this is the valence band. I already told there are many electrons present, and this is the maximum energy region of the valence band. Hence, it is called as the valence band maximum or highest occupied molecular orbital. And then on the conduction band, this is the minimum energy of the conduction band, right? So it is called as the conduction band minimum or lowest unoccupied molecular orbital. So the energy between the valence band maximum and the conduction band minimum is known as Eg. That is the energy gap or the band gap of the particular material. We will understand the significance of Eg coming on. So then in between this, in physical meaning, we say that electrons are present up to only the valence band maximum. But when we are considering different distribution theories, we will be able to understand that we need to define one thing known as the EF. What is it? EF is known as Fermi level. Fermi level can be defined as the region in between the conduction band maximum and valence band minimum in which there is a 50% probability of finding an electron, and it will be located in between the valence band maximum and the conduction band minimum. And then we have something known as ionization energy, that is the energy difference between the valence band minimum and the energy vacuum level. And then we have something known as work function, that is between EF and vacuum level, then electron affinity. Sorry, 1 minute. Okay, sorry for the disturbance. Now we'll continue. So then we have something known as the vacuum level, that is beyond the region of the crystal. So we have discussed about electron affinity, work function, ionization energy, energy gap, Fermi level. Right. So now we need to understand what each of these terms are. So what is it? The highest energy level that an electron can occupy at absolute zero temperature, as I have already mentioned, when we are considering different distribution theories, it is necessary to define a state in between the conduction band minimum and the valence band maximum, where there is a probability of finding the electron. This is known as the Fermi level. The Fermi level lies between the conduction band and valence band, and the electrons will be present in their lowest energy state. Then we have the difference between these two. I've already mentioned this is known as the energy gap or band gap. So the energy gap or band gap can be defined as the difference between the energy of the valence band maximum and conduction band minimum, and an electron can move from the valence band only if an energy equivalent to Eg is given to it. Then only it can move to the conduction band and thereby created a hole. So at least Eg should be provided so that an electron can be excited from a valence band to the conduction band. Then we have what is known as work function. So considering with respect to the Fermi level, work function is defined as the minimum energy that should be given to an electron so that it can escape to infinity from the given material. If an energy value equal to the work function is given to the material, then an electron in this region will be able to escape to vacuum or move to the surface of the solid. Then we have what is known as electron affinity. It is usually denoted by the symbol chi, and it is the energy difference between the bottom of the conduction band and the infinity level or the vacuum level. So that is the electron affinity of the semiconductor. I hope these terms are now clear to all of you. And ionization energy is the energy that has to be given so as to remove an electron directly from the valence band to the surface level or to the vacuum level. So that we have discussed all of this. First, we need to identify what is delta even. Delta even is our, what is it? It is our band gap. Delta even is our band gap. So band gap, delta even, there are two possible options, column 2 and column 4. Then we have something known as the valence band maximum to the infinity level. So valence band maximum to infinity level is what? From this particular valence band maximum to infinity level is the ionization energy. And then we have electron affinity and work function. These are the other things that we need to define, right? So electron affinity means from here to here. That is, from here to here means E2 minus E1. E2 minus E1. E2 minus E1 for electron affinity comes for column 2. And finally, we have work function. Work function we have defined as the energy between the Fermi level and vacuum level. Fermi level is located in between, therefore delta E1 by 2. Therefore, E2 minus delta E1 by 2 is our work function. I hope it's clear for all of you, and therefore our answer to this question will be column 2. This is our band gap. Electron affinity means electron affinity means from here to here. So basically E2 minus E1, and finally work function means from here to here, that is half of delta E1, E2 minus half of delta E1. So that is the work function. So all of this is matching for column 2. Sorry. And hence our answer to question 2 is column 2. I hope it's clear for all of you. So now let us move on to the next question. Creep resistance decreases due to, it was asked in GATE Metallurgical Engineering 2016 for 2 marks. So, sorry, for 1 mark. So the options are small grain size, fine dispersoid size, low stacking fault energy, and high melting point. So first we need to understand what is creep. Creep can be defined as the tendency of a material to deform slowly and permanently under constant mechanical stress and at an elevated temperature. So it is not happening at room temperature, it is happening at an elevated temperature, and the material is subjected to a constant load for a longer period of time. And under such circumstances, the material creeps. That is what happens. Then what? So when we are discussing about creep, it is necessary to define. Usually, when you are reading lectures on creep or understanding them, you'll come across a term known as homologous temperature. This is because what is high temperature for one material need not be high temperature for another material, right? So for mercury, room temperature itself is high enough; it is a liquid state. But for something like steel or aluminium, it is not high enough at room temperature. Therefore, different materials will have different high temperature based on their context, and it is necessary to like equalize all of this. That is why we usually plot creep in a case where T by Tm is measured. Tm is the melting point, so that all of these values are normalized so that we can plot the difference in temperatures. And usually creep occurs for metals and alloys when the temperature is about zero point 0.3 to 4 times of their melting point, and for ceramics it should be even more, zero point 0.4 to zero point 0.5 times of their melting point. That is the only case when materials will start exhibiting creep properties. And now we need to understand how creep resistance is affected by different properties. So before we go on to that, we can discuss some of these other, what do you call, options that are given to us: fine dispersoid size, low stacking fault energy, and high melting point. So if you see about, if you've already understood somewhat about creep from what I told, you might have known that creep resistance has nothing to do with melting point. Only thing that for a given temperature, some materials will creep, some materials will not creep, but it does not have something to do with creep resistance. And low stacking fault energy has relations with how dislocations propagate in a particular materials or how easily stacking fault defects are formed. So then low stacking fault energy is not also a choice. Then we have small grain size and small fine dispersoid size. Dispersoid size means materials that is dispersed into this solids in the molten state. So the answer should be A or B. So now we will find out which of these is more important with respect to creep resistance. Dispersoid size cannot be said as a generalized factor in creep resistance. So we'll find out which of these is the answer. So So first one is equicohesive temperature. So what is meant by equicohesive temperature? So in a material, usually at room temperature, grain boundaries are actually stronger than the interior of grains. Therefore, whenever we are trying to break the material, fracture will occur across the grains. That is, transgranular fracture will take place. But beyond a particular temperature, so what as but beyond a particular temperature, the interior of the grain is more stronger and grain boundaries become very weak. This is because grain boundaries are already regions of very high energy, and at high temperature, what happens? This high energy grain boundaries become highly mobile. That is, they will be capable of moving with respect to one another and they'll slide past one another. So what happens? Instead of cracking across the grain or transgranular fracture, intergranular fracture will take place. So at small temperatures, the strength of the grain boundary will be higher, but at high temperature, what will happen? The grain boundaries will become weaker. And at exactly the equicohesive temperature, the strength of the grain boundary and the grain interior will be same. So what we have discussed is below equicohesive temperature, fine grains are strong. Above equicohesive temperature, coarse grains are strong. Why? So finer grains means what? More number of grain boundaries. That is, we have small, many number of grains, and the grain boundaries are more in area, right? If you are calculating, grain boundaries will be more. And below this temperature, grain boundary is anyway strong. Therefore, below equicohesive temperature, finer grains are strong. And above equicohesive temperature, what happens? Coarse grains are strong because grain boundaries are already weak. So we need to try to minimize the amount of grain boundaries present. So the way in which we can minimize them is we can make larger grains, smaller number of larger grains. So, grain boundaries are therefore not desirable for high temperature structural applications. I've already mentioned they are regions of high energy. As temperature increases, they will start becoming mobile, they will slide past one another, and as a result, they will propagate the dislocation or they'll start cracking. Under normal temperature conditions, grain boundaries are stronger, they will arrest the dislocation and increase the strength, but it is not the case at high temperature as they become weaker. So when the material is loaded, the crack will propagate along the weak grain boundaries. So fine grained materials are used under normal temperature and coarse grained materials are used for high temperature applications. So with that respect, we can define the answer, right? So creep resistance decreases due to smaller grain size. Smaller grain size means grain boundary area is more. Grain boundary area is more means that creep will occur very easily. So creep resistance will reduce. So our answer is smaller grain size. This is one way of defining this particular answer. So creep resistance decreases due to smaller grain size. Yet another way of discussing this answer is we have this equation. The resistance to creep or strain can be expressed. This equation is not very familiar to people. I think that's why I give a logical explanation first. If you want a technical explanation or an analytical explanation, the creep resistance to creep or strain can be expressed as d epsilon by dt is equal to c sigma power m by d power m e raised to minus q by kt, where epsilon is the creep resistance, or we can say that this is the strain rate. C is a constant dependent on the material and the creep mechanism. M and B are also exponents that are related to creep mechanism. Q is the activation energy for particular mechanism. Sigma is the applied stress. K is the Boltzmann's constant, and T is the absolute temperature. And here we have D as the grain size. So what happens from the equation? We can see that creep resistance decreases as D becomes smaller, the strain rate becomes more. Strain rate becomes more means creep will increase, that is creep resistance will decrease. So what happens as D becomes smaller, d epsilon by dt becomes larger. D epsilon by dt becomes larger means that more creep is happening. So for smaller grain size, creep resistance will decrease. I hope it's clear for all of you. So we have both explanations. Please go through the explanations once more, and if possible, try to keep a track of at least where the values lie. For example, applied stress lies in the numerator, D lies in the denominator, and so on. Like memorizing all the equations, I think won't be easy. So please try to comprehend in a logical way. So the answer is small grain size. I hope it's clear to all of you. Now we'll move on to the next question. A plastically deformed metal crystal at low temperature exhibit wavy slip pattern line due to gate. It was asked in Gate Metallurgical Engineering 2016 for 1 mark. So in that case, we have four options: dislocation pileup, large number of slip systems, low stacking fault energy, and dislocation climb. So dislocation climb, what do you know about dislocation climb? Dislocation climb is actually the motion that is of an edge dislocation. Normal to its slip plane. There will be a slip plane and there will be a normal to the slip plane. And if the edge dislocation moves normal to the slip plane, dislocation climb is said to happen. And it is somewhat related to the addition or removal of atoms from the extra half plane of an edge dislocation. So, and usually dislocation climb will be favored at high temperature where the defects are movable and there will be more number of defects present. So, next is what I call as stacking fault energy. So, what is meant by stacking fault energy? Stacking fault energy is a material property on a very small scale and it is the energy per unit area. So, stacking fault, we also know stacking fault that is FCC, BCC, etc. They will be having a particular arrangement if we have seen like ABAB, ABC, ABC, and so on. So, whenever there is a disruption in this particular stacking, it is known as the stacking fault energy. So, and stacking fault energy, are they important to plastic deformation? Well, stacking fault energy, I think it basically depends on the free electron density distribution. That is like bigger concepts, I would say. And usually, the case is that lower stacking fault energy means that dislocations will be less mobile and less number of stacking faults will be there in a particular slip plane. And if we have gone through the concepts of stacking fault defects and cross slip incline, lower stacking fault energy materials will have wider stacking faults and they have more difficulty in carrying out cross slip and climb. Therefore, we can say that stacking fault energy basically modifies the ability of a dislocation in a crystal to glide onto an intersecting slip plane. That is when by stacking fault energy. There are large number of slip systems and dislocation pileup. So dislocation pileup, basically what does it mean? So whenever there is a point defect or some kind of an entity or a precipitation hardening precipitate or in precipitation hardening or cold working, etc., some kind of deformation is taking place, and in the grain boundary or at the defect, etc., the dislocations will start piling up and the material will be strengthened in that particular manner. So that is dislocation pileup. Large number of slip system means that all materials will be having different slip systems, and based on the value of the resolved shear stress on these slip systems, a material will be subjected to deformation or not. So which among these is responsible for the wavy slip line pattern in a material? So if we see here, so this is a material that has been subjected to some kind of a tension or so. And if we have seen my previous session, you might have understood what is meant by slip plane, slip direction, and normal to the slip plane. And in this case, whenever a material is subjected to a tension or a torsion or whatever kind of an what do you call, when we are applying a stress to it and the material is deforming under the stress, the atoms in the material will move a particular distance each time, and it is an integral number of atomic distance that is along the slip plane, resulting producing small steps, and each of these steps will appear as a line known as the slip line, and the slip lines will together form a pattern as shown here, and together they are known as slip bands. So slip does not occur just on one plane but on very small regions of parallel planes, resulting in number of slip lines. See, in a material there are many slip systems, right? Slip systems means a combination of a slip family, that is a family of planes and a family of directions. And however we are applying the force onto the material, there will be always resolved shear stress. And when the value of this resolved shear stress reaches a critical value, deformation or slip will start propagating on that particular plane, and hence there are multiple slip systems. These propagations will start and hence multiple slip lines will be formed, and together they will form something known as the slip band, sorry. So this is the slip band width. So slip line patterns are lines that appear on the polished surface of a crystal or crystalline body which has been stressed beyond its elastic limit. So basically what happens is that it represents the intersection of the slip planes on the surface of the material. Intersection of surface by planes on which shear stress has produced a plastic slip or gliding. So that is one by slip system. So that is what happens when we see
Slip line patterns. So as I already mentioned here, it's mentioned slip line. What is slip system? Slip systems means a family of planes and associated directions on which dislocation occurs. So basically, whenever a dislocation occurs on a particular material, slip lines will be produced, and this slip lines will have different, you know, a wavy line-like pattern will be there. So why are these line-like patterns? As I've already mentioned, there are large number of slip systems inside the material, and for different values of critical stress or shear stress, these dislocations will start moving, or we can say slip will be initiated, and the slip will be initiated back to back, and the atoms will start moving integral number of lines, and together, when we see macroscopically, they form a wave-like pattern. So the reason for the wave-like pattern is the large number of slip systems that is present in a material. So therefore we can say a plastically deformed metal crystal at low temperature exhibits wavy slip line pattern due to the large number of slip systems present in the material. So that is the answer to this question. I hope it's a rather direct explanation, I would say, if you are familiar with the concepts of slip band theory. So that is all about today's four questions. I hope all of you have understood the essence of these questions. Please go through these questions before gate examinations, and in case you have any additional queries and feedback, or if you would like to request me for a special session, etc., please do email me at santra.pmrf@gmail.com. So that is all for this week. I hope all of you are benefiting from these particular sessions. So thank you for your time. Thank you so much. See you next week. Bye bye.